All right, so we are going to go on a geologic tour of the Timpanogos cave system today. So a little bit of background on this cave system. This cave system is actually part of a national monument in American Fork Canyon, so pretty close to where I actually grew up. I actually worked at Timpanogos Cave for a little bit, so a lot of this information is going to be coming from my previous experience, and then some more of it will be coming from resources that I have studied over the last couple weeks. So to start off with, the rock that the Timpanogos Cave system is in is called Deseret limestone. So it is a type of limestone, but it's a very dolomitic limestone, which is what gives it this very dark color. When it has been exposed to weathering, like you see on this picture on the left, it becomes a little bit more of like a light color just because it has been exposed to the elements, erosion, things like that. But if you were to break off a piece, it's dark, like black limestone, which is not all that common. Also, in this limestone, it's very calcium heavy. In fact, there are lots and lots of fossils in this limestone, and that's what you're seeing up there in the top right hand corner picture. That is a rugose coral fossil, so lots and lots of coral fossils, which there again shows us that this rock was formed at the bottom of a warm, shallow sea many years ago. So that's the layer that the cave system is formed in. If we want to see what that's like in comparison to the rest of the canyon, here is kind of a map of the different layers within the canyon. So Deseret limestone is not at the very bottom, it's also not at the very top. There's lots of like that tinted quartzite like we saw at the bottom of Rock Canyon. There's some of that there. Probably the same layer just stretching to the next canyon over as well. And then we've got some limestone, we've got lots of slate and other minerals mixed in there as well. Lots of sedimentary minerals. And then you get about halfway up the canyon, and that is where you see the desert limestone layer with the cave system in it. So how did the cave form? This is one of my favorite chemical processes. It's one that's easy for me to remember. I recited it many times giving cave tours. But it starts with water. So you get rainwater coming down from the surface, or like melted snow. And as that seeps through the soil layer up top, and then all the rock layers, it's actually going to pick up a little bit of carbon dioxide from the soil, from decomposition of plants, things like that. But when it picks up that carbon dioxide, it becomes carbonic acid, which we know is like soda pop. It's just like carbonation, right? But kind of like you can kind of think of it in the same way of like when you drink a lot of soda, it wears down your teeth, right? It's because that carbonic acid dissolves calcium. So think back to the limestone, right, and to that fossil. When that solution right there, that carbonic acid hits that limestone layer, it actually starts to dissolve out the calcium. And then as it continues to seep through, it's carrying those calcium crystals with it. But then when it hits the cave, which is this space in the mountain, the soda goes flat, pretty much, right? It loses, and this next slide here, it loses that gas, right? And then it releases the calcium crystals as well, which is where we get cave formations. It turns into just like water, a little bit of carbon dioxide, that's what gets released, and then calcium carbonate is the crystals that the formations are made out of. So we get lots of different formations. In this picture, we see a lot of stalactites, which are the ones that are hanging from the ceiling. Stalagmites are the ones that come up from the floor. There's no like difference in chemical structure or anything like that, or crystal structure between the two. It's just where they formed, where the water happened to be running. However, we will see in a minute how different crystal structures in different formations causes a color change. Not necessarily like a chemical formula change, but a color change and how it's manifested. Excuse me. So when we get just straight calcium carbonate, it's usually a pretty white color, right? Sometimes it'll be a little bit creamy, but it's very just white. We get the fun colors when we get different minerals mixed into it. So I put some of my favorites into this presentation. In this slide, if you look to the far, like kind of the middle left, you see a big stalactite coming down that's almost like an orange pinkish color. And that is from manganese deposits. So manganese typically will form, if it's in high concentration, it'll actually form purple. which would be very, very dark. But then in lesser concentrations, it's more of a pink, and then it fades into, this is very little manganese, and so this is more of just like an orange or a light pink. When we get nickel deposits in the calcium carbonate, it turns this really pretty yellow. In fact, there's parts of the cave that if you shine a light behind it, it looks like a lemon. It's so yellow. It's kind of cool there. Pay attention here though. This next slide that we see, this is also calcium carbonate with nickel deposits, but now it's green. Kind of cool. Why does that happen? So it's the same calcium carbonate, right? CaCO3, but the difference here is the crystal structure. So with the yellow that we just saw, that is in the crystal structure of calcite, whereas the green that we see here is the crystal structure of aragonite. So same chemical formula, CaCO3, but just the way that the crystals form has to do with the evaporation process and like that. It'll actually shine a different color, even though it has the same minerals in it. There's another color inside the cave that is more of like an orange, and it can turn into a deep red as well. You can probably guess that's from iron, right? It's just rust. So that iron comes in with the calcium carbonate, and then as it hits the oxygen in the cave, it rusts and turns this beautiful orange color. In fact, this particular part of the cave we like to call Caramel Falls because we've got so much of that red running down. So that's kind of the basis of how caves form, but one very important part that I've left out so far is the importance of plate tectonics in cave creation, especially in the Timpanogos cave system. The Timpanogos cave system is actually formed completely along a fault line. So if you look at this map here on the right, you can see that the cave is pretty straight, right along that diagonal line, right? That is the fault line. Water takes the path of least resistance, right? We've learned about that when it comes to rivers, like when they carve out canyons and things like that. Water wants to go in the path that takes it downhill with gravity, right? And usually with least resistance, so like a crack. So we had this fault line that shifted, right, causing a crack in the earth, and so that's where water went in initially. Came down, dissolved out this cavern space, because the desert limestone is a little less dense and a little bit more soluble, a little bit more dissolvable than the rock around it. So carved out this beautiful cavern. At that point though, fun fact, the cave was still beneath the water table. So this big opening hollowed out with water churning inside there. It wasn't until more tectonic movement, the cave was lifted up above the water table, that the water drained. So now when water comes in, it's able to form the cave formations rather than just churning with all the rest of the water. So why does all of this matter? Why do caves matter to me? Why do caves matter to any of us? There's a few reasons. Caves are unique in that they are some of the few places on Earth that people haven't stepped or they haven't explored completely, right? Most land masses we've discovered, right? We have been able to explore to the extent possible, but caves are areas beneath our feet that a lot of times we don't even know exist until enough erosion happens that an entrance opens up. And only then can we go in and explore this land beneath our feet. Caves are unique as well in that they are very isolated. So every ecosystem that is inside of a cave, that's its own ecosystem. It typically won't share that same ecosystem with any other cave even across the world. So it'll have its own bacteria, it'll have its own organisms, its entire little world there in the cave, which brings about a lot of scientific possibilities. There have been caves discovered in southern United States where bacteria has been found that could be the cure for cancer. They're doing research on it right now to try to see if they can transport it outside of caves, because they have found that it attacks and kills cancer cells without harming normal body cells. Kind of cool. Another reason that caves are really important is they do hold a lot of water, especially the ones that are still beneath the water table that haven't drained yet. A lot of our water that we drink comes from underground water systems in caves and things like that. So caves are super important, not only to protect, but also to study, because we do not know all of the amazing discoveries that we can pull from caves beneath our feet. Thank you so much.